So today I'll be talking about the production of ATP, NADH, and FADH2 for the Advanced Concepts Presentation 5. The overview of this presentation is that I'll go step by step and note how in each part of aerobic respiration, ATP, NADH, or FADH2 is produced. At the end, I'll talk about the conversions between NADH to ATP and FADH to ATP, as well as the net yields of ATP at the end of aerobic respiration. So first, in glycolysis, we lose 1 ATP when the glucose is phosphorylated by hexokinase. So here we see the ATP molecule that is used to phosphorylate the glucose, which then turns into glucose 6-phosphate. So here we've lost 1 ATP. Another ATP is lost during the phosphorylation of fructose 6-phosphate. The enzyme responsible for this is phosphofructokinase, and the product is fructose 1,6-biphosphate. So again, we see this ATP being used in the reactants, and we lose 1 ATP. Where we begin to gain ATP is in the dephosphorylation of 2 molecules of biphosphoglycerate, or 1,3-biphosphoglycerate, or 1,3-BPG. So the enzyme responsible here is phosphoglycerate kinase, and we see that the phosphate group is lost, and we get a 3-phosphoglycerate. In this reaction, the 2 molecules of 1,3-BPG yield 2 molecules of ATP. Another place that we see the gain of 2 ATP is in the dephosphorylation of PEP, or phosphenylpyruvate. The enzyme responsible here is pyruvate kinase, and we can see this occur in step 10. So we'll see this reaction another time, but here I'm highlighting step 10, where PEP is dephosphorylated. You see this red group leaving to give us pyruvate. And here ATP is created. In fact, 2 ATP come from this reaction. Another place we see some gain is with NADH. So the oxidation of G3P forms 2 NADH molecules. So we see that right here in step 6. So the enzyme responsible here is glyceraldehyde 3-phosphate dehydrogenase, or G3P dehydrogenase. And in this reaction, 2 molecules of NADH are formed. When we continue on, we have pyruvate being made into acetyl-CoA to get ready for the citric acid cycle. And NADH is formed in this step as well. So through the oxidative decarboxylation of pyruvate, 2 NADH molecules are created, plus carbon dioxide. When the acetyl group links with the coenzyme A, it creates acetyl-CoA, and this is going to be the fuel for the citric acid cycle, which we'll step into next. So here we've made 2 molecules of NADH. Now we're in the citric acid cycle. Here's a picture of it, and I thought this was a really good visual of what the citric acid cycle looks like and what products are being formed. So we see that NADH is formed in this in these reactions in this cycle, and so we see 3 NADH. So there's actually going to be 2, there are 3 NADH, and we have to multiply by 2 because 2 molecules of pyruvate have been formed. So we're going to double all of this. So this is going to be 6 NADH in total. And then the same goes for FADH, and 2 FADH2s are going to be formed, as well as 2 ATP molecules in this reaction. The 2 molecules of ATP come from succinyl coenzyme A, and then the 6 molecules of NADH are from the oxidation of isocitrate, which is here, and let's see, from the alpha ketoglutarate and malate. So I'll point that out. So malate and alpha ketoglutarate. In these 3 steps, isocitrate, alpha ketoglutarate, and malate, NADH is formed. Last, with the FADH2, FADH2 is from 2 molecules of succinate, so we'll have 2 molecules of FADH2 be formed in the citric acid cycle. Now we reach the final stage of cellular respiration, and that is oxidative phosphorylation, that is made up of the electron transport chain and chemiosmosis. So in this step of cellular respiration, we see a high yield of ATP in various steps. So in the next slide, we can look at the amount of ATP that is yielded and NADH and FADH2 in each of these steps. So with glycolysis, for 1 NADH, 1.5 ATP are formed. And so with 2 molecules, you'll have 2 NADH and 3 ATP in full. So we'll use that principle throughout, just doubling for each product. In oxidative decarboxylation, you have 1 NADH, which yields 2.5 ATP. So when we double it, for every 2 NADH, 5 ATP will be formed. Then, in the citric acid cycle with FADH, for every 1 FADH2, 1.5 ATP is formed. So when we double, for every 2 FADH, 3 ATP are formed. Last, again in the citric acid cycle, now concerning NADH, for every 1 NADH, 2.5 ATP are formed. And so what we saw earlier in the Krebs cycle is that there are 6 NADH in total. So when we multiply 2.5 times 3, you get 15 ATP. So after we add all of these numbers together, we get a net yield of 30 ATP. And here is the molecule of ATP, and this is from aerobic respiration. Thank you.